Here is the next example on the mutual inductance. Here he's asking about write two loop equations for the given circuit. All we need to do is write down the two loop equations. So remember, we have dots and mutual inductance. So because of the mutual inductance, there is an induced EMF. Mutual inductance is nothing but if current is passing through one coil, okay, there is an induced EMF in the second coil. That induced EMF I am indicating with E equal to, assuming that there is a mutual inductance M, E equal to Jm times I1 in the frequency domain. Okay, so now which one is positive, which one is negative, we can find out by using the dot convention. So according to the dot convention, if current is entering the dotted terminal of the first coil, then the dotted terminal of the second coil will be positive. So for example, here is a dot and here is another dot. So this dot indicates that the orientation of the coil. So probably this coil might be wound in clockwise direction. Another coil, the second coil, might wound in the anti-clockwise direction. So that's the reason dots are opposite side. So here the current I1 is entering the dot. So the dotted terminal is going to be positive. So the induced EMF across the second coil will have a positive terminal down here. So in the same way, I didn't write down the second statement. If current is leaving the dot, so here is my I1, that this indicates that current is going out of or the dot is at the end of the inductor. If current is leaving the dot, then the dot terminal is going to be negative. So here I'm going to have negative, positive, EJMI1. Okay, these two examples are two different examples. If current is entering the dot, the dotted terminal is going to be positive. If current is leaving the dot, the dotted terminal is going to be negative. All you need to know these two to write down these two equations. Now step 1, I'm going to write KVL in loop 1, KVL in loop 1. Okay, according to my I1 direction, I'm going to assign positive and negative sign, positive, negative, positive, negative. Now each coil has a mutual inductance with another coil. So let me take this as L1, L2, or let me take this as L2 and this one is L3. Okay, that's L3. Now if you look at coil L1, L1 has two mutual inductance. So there will be two EMFs induced across this coil. Same thing here, L2 is also involved, two mutual inductance. So it will end up having two induced voltages. So let me write down loop 1. The normal equation is minus 12 at an angle of 0. By the way, the given circuit is in frequency domain, so we don't need to convert anything. Current is entering the negative terminal, so that's the reason I'm taking that as a negative voltage, plus J5 times I1. Loop 1, I'm taking this current as I1, plus J6 times I1 minus I2. This is our normal mesh equation. But because of the mutual inductance, there is a mutual induced voltage across each coil. Now we have actually two mutual voltages induced across L1 and two mutual induced voltages across L2. So across L1 there are two of them. I'm going to label them as E1 and E2. Here I'm going to label them as E3 and E4. Okay, so E1, E2, E3 and E4 equal to 0. Now we have to find out which induced voltage or now we have to find out which one is positive terminal, which one is negative terminal of that induced EMF. So here if you look at E1, okay, I'm going to assume E1 is induced voltage across L1 because of current passing through L2. So as I mentioned, E1 is induced EMF across L1 because of current flowing in L2. Same thing, E2 is induced EMF across L2 because current flow in L3. E3 is current induced EMF across L2 because current flow in L1. E4 is current induced EMF across L2 because current flow in L3. So let me find out E1. E1 is nothing but induced EMF across L1 because current flow in L2, which is nothing but the mutual inductance is J8. That's what I have. The mutual inductance is J8 times what is the current flowing in J6, the L2. Current flowing in L2 is I1 minus I2. Okay, that's E1. And induced EMF across L1 because of current flow in L3 is, what is the mutual inductance between L1 and L3? J2, and current flowing in L3 is I2. So this is J2 times I2. Now induced EMF across L2 because current flow in L1, the current flowing in L1 is I1. Okay, now the mutual inductance is J8, so this is J8 times I1. The last one is the mutual inductance between these two is J2 times I2. Current flowing in that L3 is I2, so that's the reason it is J2 times I2. Now you have to find out which terminal is positive, which terminal is negative. So here across L2, J8 times I1 minus, the induced EMF across L1 because of current flow in L2, J8 times I1 minus I2. So I1 minus I2, we have to look for this dot. I1 minus I2 is leaving the dot, so the dotted terminal must be negative. So this must be negative, this must be positive. For I will do the E2 also. E2 has current is entering the dot, so the dotted terminal must be positive, negative. So if you look at here, this positive here, the green one, is induced EMF because of the self-inductance. This is induced EMF because of current flowing in L2. E2 is because of current flowing in L3. So E1 must be negative because it has opposite sign. So E1 must be negative, this must be positive. E2 must be positive because whatever the voltage because of this and because of this, these two are going to add, E1 must be subtracted from it. Now we'll do E3 and E4. So if you look at E3, because of the current flowing there, induced EMF here, so current is entering the dot, so the dotted terminal must be positive. So E3, we're going to have positive here, negative there, and E4, current is entering the dot, so I2 is entering the dot, so the dotted terminal here must be positive, so your E4 will have that is positive, this is negative, this is E4. Okay, so here also E3 is going to be negative because it has the opposite sign. So E3 is going to be negative, E4 is going to be positive. That's our first equation. So let me rewrite first equation. Okay, so here is my complete equation after including that induced EMFs. Okay, that's our equation 1. Now, as I mentioned, you can do this in a different manner. So let me write it down here. So here is my, I'm going to write down the first loop. Here is my source, okay, to avoid that mutual. So I have E1 and E2, so I'm going to put E1 right there, E2 right there, and here also I have E3 and E4. Those are all dependent sources. Okay, so this indicates E1, this indicates E2, this indicates E3, this indicates E4. Okay, so now I don't need to indicate that arrows and mutual inductances. So this is J5, here is my I1. Of course, there is loop 2 here, loop 2 has I2. I'm not worried too much about that. So E1, which one is positive? E1, I end up with this terminal is negative and this terminal is positive. So negative, positive. E2, this terminal is positive and this terminal is negative. And E3, I have negative, positive. E4, positive and negative. What is E1? E1 is J8 times I1 minus I2. E2 is J2 times I2. E3 is J8 times I1. This is J8 times I1. And E4 is J2 times I1. So this is another way. What I'm doing, I'm representing that induced EMF as a dependent source, current dependent voltage source. I'm representing that mutual inductance or induced EMF because of mutual inductance by a dependent source. Now here I don't need to indicate the dots. The dots are already replaced with that dependent sources. Okay. Now you can write down the equation. When you write the equation, you should end up with the same equation. So this is another way of writing down the equation. Now I'm going to write down the second equation for loop 2. So for loop 2, according to my I2 direction, I'm going to have plus and minus sign, plus minus, plus and minus sign. Okay, this is my loop 2. Now according to loop 2 current direction, apply KVL. And also, okay, I already assigned. So J10 times I2 plus 5 times I2 plus J6 times. Whenever I'm in loop 2, I always assume current is I2 is larger than I1. J6 times I2 minus I1. Now, how many mutual inductances are there, or mutually induced EMFs are there? So because of the current flowing in L1, there is an induced EMF here. I will take that as E1. I don't know which one is positive or negative. Now because of the current flowing in L2, there is an induced EMF across this. I'm going to take that as E2. Now same thing here across this coil. Okay, across the L2 coil, because of the current flowing L1, I have an induced EMF E3, and because of the current flowing in L3, I have induced, I don't know the positive or negative yet. So, and E4. So those are the 4 voltages. Now we need to find out which one is positive, which one is negative. Let me put E1, E2, E3 and E4. Okay, now when it comes to E1, current flowing, to avoid confusion, I removed the first E1, write it down because of the loop 1, induced EMF in the loop 1. Now E1 right here, the E1 equal to, because of the current flowing, here the current is entering the dot, so the dotted terminal must be 0. The dotted terminal must be positive, so this must be positive, this must be negative. E2, here the current, it's up to you. You want to take I2 minus I1 or I1 minus I2. Whenever I'm in loop 2, I usually go with I2 minus I1 to avoid confusion. My I2 minus I1 is leaving the dot, so the dotted terminal must be negative. Okay, so that's my E2. So E1, these two have same sign, so this must be positive, and E2 has negative sign, so let me take that as E2 as negative. E3, when it comes to E3, current flowing in here is entering the dot, so the dotted terminal must be positive, so E3 will have positive and negative there. E4, current is entering the dot, so dotted terminal must be positive and negative. So E3, this will have negative, this will have positive. Okay, so what is E1? Because of the first coil, which is J2 times I1, and here this is J2, that is also J2 because of the current flowing, or the mutual inductance here is J2 times I2 minus I1, and E3 equal to, because the current flowing there induced, E3 I chose this because the current flowing here. Okay, E3 equal to J8 times I1, and E4 is, because of the current flowing there, induced EMF, which is J2 times I2. Okay, so this is the second loop equation. Okay, I will stop it here in this video. I'll solve more examples in the next video. Thank you.